Hi, so today we're going to be looking at a problem on quantum mechanics. Well, this is a really standard problem in which we're given the Hamiltonian and we have to find the time evolution of some initial state. Well, just really quickly, we know that when we have a system, a quantum system, it is described by the state psi in general. And this state has to satisfy the Schrödinger equation. And if we're given an initial state, t0, in this case t equals 0, then we can solve the Schrödinger equation. And to do it, we have to solve the time-dependent Schrödinger equation. This will in general give us the expression for the time evolution of the state, which is just the sum of, well, this term here, which holds the time evolution, Cn and phi n, where Cn is just phi n times our initial state. But phi n and En are the eigenvalues and eigenvectors of the Hamiltonian, which are found in the standard way of, well, we just have to take the determinant of this, find the eigenvalues, and then just find the kernel of each eigenvalue, which is just the eigenvectors, by solving a system of equations. To see this, let's just do it really quick, and you'll see what I mean with this. So, we have to solve, we are given the Hamiltonian, and we want to find the time evolution of an initial state. So, as we said, we need to find our eigenvectors and eigenvalues. So we solve the eigenvalue problem for the Hamiltonian. So we have to take the determinant of h, but it's h minus e times the identity. And the identity only has terms on the diagonal. So we have this. If we take the determinant, we get that, well, e minus e squared times, c minus e minus b squared times c minus e is just 0. We're imposing that it is 0. So this will hold. Notice that if e equals c, let's just call this e1, equals c, this term goes to 0 and this term goes to 0, and well, the equation is satisfied. So this is our first eigenvalue. Now, what happens if e is not 0? Well, in that case, we can divide by c minus e because this term is not 0. So we'll end up with these two terms cancelling out, and we have this equation. Now, from this, we can of course just write like this, putting this square on the other side, and by taking square roots on both sides, we will get that, well, the absolute value of this is equal to the absolute value of this, and we can just write this easier by putting a plus minus sign here. From this, we get two new eigenvalues. E2 is a, yes, plus b, and E3 is just a minus b. So these are our three eigenvalues for the Hamiltonian. So let's just write them right here. Let me just erase this and we will find the eigenvectors. As you see, it's not too hard to find the eigenvalues of the Hamiltonian when we're given the Hamiltonian in matrix form. Now, what are the eigenvalues associated with E1 equals C? Well, we have to solve this system of equations, which is just, well, a minus E1, 0, b, 0, c minus E1, 0, b, 0, and a minus E1. Times our eigenvector, we'll just call it phi 1, or phi in general, maybe we have more than one, phi, and well, we'll have components alpha, beta, and gamma. We're imposing again that this is 0. Well, we know that E1 is just C, so let's just substitute here. But C minus C is just 0, so this is 0, and A minus E1. Notice that this is a representation of a system of equations, but this really is just all 0, so we don't even care about that. Because it will just give us 0 equals 0. So let's just do this. A minus C alpha plus 0 beta times B gamma equals 0. This is just 0 times this equals 0. Let me just write it. And the last one is B alpha plus 0 beta plus A minus C gamma. From this we get that, well, alpha is just, you can express it as minus A minus C over B, assuming that B is not 0. If B was 0, then this would go to 0, and gamma will have to be 0, and alpha will have to be 0 in this one, and we'll get actually the same result as you'll see later. So let me just assume that B is not 0. Or even easier, we don't even have to assume this, and we can just well, let's just assume that B is not 0. Let's just assume that B is not 0, and we'll see that it's easier after it. Okay, so this is what we get. Substituting on the first equation, we get that minus A minus C times this, we just give us a squared over B, plus B gamma is equal to 0, and this is a gamma, sorry. We can multiply by B, and we get that B squared minus A minus C squared times gamma is equal to 0. In general, we have that this term is not 0, because for this term to be 0, we will need that B squared equals to A minus C squared, which is just that A minus C is equal to plus minus B. But we said that A minus C is not plus or minus B. So this in general is not 0. So the only way that this can hold is if our parameter gamma is in fact 0. This implies that alpha is also 0. And what about beta? Well, really, all these equations will hold for any value of beta. So we have that their eigenvector, is just alpha, beta, and gamma, but alpha and gamma are 0. So we have this. And beta really can have any value because it will not influence our system of equations. So what we have is that we have an infinite set of vectors where beta is a real number, and all of these are eigenvectors of this eigenvalue. What do we do then? Well, we choose the eigenvector with modulus 1 or with norm 1. And to do that, well, you see that if we choose beta equals 1, we can say that our first eigenvector is just 0, 1, and 0. This is our first eigenvector. And it has norm 1 because, well, just do it and you see that this vector has norm 1. So, our first eigenvector is just 0, 1, and 0. Let's go for the second one. So, in our second one, I'm gonna, let me just erase all of this. So we will do the same for the second eigenvector, and let's see what we get. Sorry, it's just 1 and 0. We have chosen this eigenvector. We could choose any other one, but we have to divide by the norm, and we have to divide that eigenvector again. So instead of C, well, E2 is A plus B, so we have A plus B, but this is just minus B. C minus A plus B, and A minus A plus B is just minus B again. So we get minus B alpha plus B gamma equals to 0, C minus A plus B times beta equals to 0, and B alpha minus B gamma equals to 0. From this, well, in general, as we said, C is not equal to A plus B, in general. No, in fact it isn't, because if A minus C is not B like this, then we have that C cannot be A minus plus B. So this in general is not 0, so for it to hold, we necessarily need that beta is 0. Now, from the first equation and the second one, which are really the same, we have that alpha equals to gamma. So we already have our second eigenvector, and we can express it as follows. Well, we have alpha, this has got to be 0, beta is 0, and gamma. But gamma is just alpha again, so we can write this as alpha 1, 0, and 1. And out of all these eigenvectors, right, because alpha is a parameter, we need the one with modulus 1. So we will choose that alpha is 1 over the square root of 2, because that is the modulus of 1, 0, and 1. So our second eigenvector is 1 over the square root of 2, 1, 0, and 1. And for the last one, we will do the exact same. And let me just erase this. And let's just do it. And after this, really, this is just pretty straightforward. There's no mysteries. So A minus A, sorry, this is not a C, this is a B. A minus B, C minus A minus B, and A minus A minus B. Again, well, in this case we get plus B again, and here, well, we get that term just. In this case, alpha plus gamma beta is 0, C minus A minus B beta is 0, and B alpha plus B gamma is just 0. In this case, once again, C is not A plus B. A minus B cannot be, so beta has got to be 0 again. And in this case, alpha is actually minus gamma. So our eigenvector, in this case, is alpha 0 minus alpha, and this is just alpha 1, 0 minus 1, and choosing again the one with norm 1, we get 1 over the square root of 2, 1, 0 minus 1. And I just erase this. So our third eigenvector is just 1, 0, and minus 1. And I just want you to notice some things. Usually when you calculate the eigenvalues of the Hamiltonian, a nice way to check if you have actually done it right, it will not ensure you that you will have done it right, but it's something that should hold. You have to do the dot product between the vectors. They have to be orthonormal, right? So phi 1 and phi 2 are orthonormal, really. They are perpendicular. Phi 1 and phi 3 are also perpendicular, and these two, phi 2 and phi 3, are also perpendicular. So, and they all have real values. And the eigenvalues are real values. Okay, because they are values of the energy, they have to be real. So it seems that everything is correct. It doesn't mean that it is correct, but it just means that it makes sense. So now that we have the eigenvalues and eigenvectors, how do we find the time evolution S of our state? Well, let's just call it, well, we can really just call it x of t. And this is the sum over all n of Cn e to the minus I and t minus t0 over h times the eigenvector, sorry. Now, let's just split this into various parts. What are all our eigenvectors? Well, our eigenvectors are really just phi 1, phi 2, and phi 3. And the thing is that they constitute a basis of our Hilbert space, an orthonormal basis of our Hilbert space. And in this case, our Hilbert space is C3. Okay? So it makes sense that we need 3 orthonormal vectors to make a basis of this space. So that's what we have. And well, so if we only have 3 eigenvectors, n will go from 1 to 3, because we don't have any more. So we will have to go from 1 to 3. If there were more eigenvectors, we would need to put here more, a bigger number. So, well, this is nothing but C1 times e to the minus I E1 over, and just really quickly, T0 in this case is just 0, so we don't need the T0, just write T over h bar, which is the normalized Planck's constant, and phi 1 plus C2 e to the minus I, in this case 2, h bar phi 2 plus C3 e to the minus I h3t h bar phi 3. Okay, let me just erase this. But okay, we know actually everything except C1, C2, and C3. So C1 is nothing but the dot product between phi 1 and our initial s. So let's just do it. This is just the dot product of phi 1 times, well, what is s? Really notice that s is just phi 1, because they are both 0, 1, 0. So we can just write this as the dot product between phi 1 and phi 1, and this is just 1. So here we can just write a 1 and really just don't write anything. This is our first term. Second one, C2 times phi 2 times, instead of S0, we can just write phi 1. As we said, they are orthonormal, right? So let me just do it really quick. When we have to do the dot product, instead of writing the column vector, first we write phi 2 as a row vector, 1 over square root of 2. And we just have 1, 0, and 1 times our column vector phi 1, 0, 1, 0. And this is just 1 over the square root of 2. Sorry. Of, well, this times this. 1 times 0, 0 plus 0 plus 0, this is just 0. So they are in fact orthonormal. So C2 is 0. And this is 0. And the same happens for C3. If we do it, we get that phi 1 and phi 2 are 0 too. So we have that this is also 0, and we have that the time evolution really is just given by this term. Let me just write it a bit cleaner here, and we'll go on to the next part of the exercise. So the time evolution of our state is nothing but E minus I E1, sorry, E1t over h times phi 1, and what is phi 1? Let me just write it at 0, 1, and 0. But what is E1? E1 is just C, so instead of writing E1, we can just write C. And this will be our solution. Okay, so the next part of our exercise is to find the time evolution when we have another initial state, in this case 0, 0, 1. So we have to do the same. We have that the time evolution is just the sum over n, which we know is n going from 1 to 3, because we already have the eigenvectors and eigenvalues of our Hamiltonian, of Cn e to the minus I Ent, because in this case we already have that T0 is 0 again, h bar phi n. So we have to find Cn. So this is really easy. C1 is just phi 1 times S0. So to do this, we put phi 1 as a row vector, 0, 1, 0, and we multiply it by S0, which is a column vector. So this will give us 0 times 0 plus 1 times 0 plus 0 times 1. This is just 0. So C1 is just 0. They are orthonormal. C2 is just phi 2 is 0 again. And well, phi 2 just has square root of 1 over square root of 2. And we have that 1, 0, 1 times 0, 0, 1. Just notice that when we write a ket, which is just like a bra, a ket is like this, and a bra is, sorry, the other way around. This is a bra and this is a ket. When we write a bra, what we have is that we have to take the transpose conjugate. So we have to transpose our matrix, put it as a column vector, and take the conjugate. But in this case, everything is real numbers, so we don't care. So we have 1 over the square root of 2, 1 times 0, 0, 0 times 0, 0, and 1 times 1 is just 1. So we have that this is C2, and C3 is just phi 3 is 0, and we have 1 over the square root of 2, 1, 0, minus 1 in this case, 0, 0, 1, and this is just minus 1 over the square root of 2, and that's it. So the time evolution in this case is just C1 is 0, C2 is 1 over the square root of 2, e to the minus I e to t, h bar and phi 2 minus, because we have that C3 is minus 1 over square root of 2, minus 1 over the square root of 2 of e to the minus I e3 t h bar, like this. So this would be our solution. So let's just write it a bit nicer and we will be done. So the time evolution is just 1 over the square root of 2 of e to the minus I. E2 is just a plus b, so we can just write a plus b t over h bar times phi 2. And yes, phi 2 is just 1 over the square root of 2. All of this, so we have 1 over the square root of 2, 1, 0, 1, like this. So this times this is just 1/2. Sorry. And minus 1 over the square root of 2, e to the minus I, a minus b, t over h, times 1, 0, minus 1. We have another 1 over square root of 2, so this becomes 1/2. And this would be the time evolution of our system. And well, we actually can simplify this a little bit. So let's just say that we write this all in one term. Just erase this. So we can just write this as xt. Well, just take the 1/2 and write, well, e to the minus e, a plus b, t over h, and likewise e to the minus e, a plus b, t over h, and well, this is just 0, minus e to the minus e, a minus b, t over h. Here just plus, right? Yes. E to the minus e, I, sorry, yeah. And this is what we get. So we can actually just rewrite this using Euler's formula as follows. Let me just check that I wrote everything correctly. Yes. So in both terms we have well, e minus a plus b t over h is just e to the minus e a t over h times e to the minus I b t over h. Likewise, this term right here, sorry, is a minus b t over h, which is just e minus a t times e to the I plus I b t h. This term is common in both terms of a vector. Just notice that this is a 3 vector. It's 1, 2, 3. It's not that we have various components, it's just that this is a long sum. So we can take out the e to the minus, we can just write it like this, 1/2. We can take out e to the minus iat over h, all the terms, e to the minus at over h, and we end up with e to the minus ibt over h minus e to the I bt over h, 0, and e to the minus bt over h, e to the plus I bt over h. So let me just erase this. And we know that the cosine of, let me just call it theta, is just e to the I theta plus e to the minus I theta over 2, and that the sine of theta is just e to the I theta minus e to the minus I theta over 2i. So we can rewrite this in terms of cosine and sine. This really is just, if we call theta equals to bt over h, we have that this is the cosine over 2, sorry, this is twice the cosine, and we have 1/2 over e to the minus I at over h of the twice the cosine of bt over h. This will be 0, and in this case we need to switch around, so we'll have minus the sine of theta times 2i. So we have minus 2i times the sine of bt over h, and this is nothing but our final solution would be just, well, we can take out the 2, and we have e to the minus iATH over minus I sine bt over h, 0, and the cosine of bt over h. This would be our final solution. So, well, I hope you enjoyed the video. This was a really easy exercise on quantum mechanics. We'll be doing a lot more of quantum mechanics problems. So, see you in the next video.